my name's Logan, and welcome back to the lecture hall. Today we are doing the second lesson of single variable calculus, section 1.2, mathematical models, a catalog of essential functions. So what is a mathematical model, you may wonder? Well, it's a mathematical description of how something works in real life. So a few examples would be the size and growth of a population, the speed of a falling object, and the trajectory of a rocket. Essentially, mathematical models are a necessity when it comes to real life. I know people tell you, oh, there's no point for math in the real world, but there is, more than a lot of people know. So the first type of model we're going to look at is the linear model. It's the easiest form of a function, and we have been doing this since Algebra 1, but a linear model is a line. So when you have the graph, it's just has a y-intercept, and the equation of the line is equal to y equals mx plus b, where the m is the slope, the rise over run, and the b is your y-intercept. So for the example 2x plus 1, it would look like you have your y-intercept at 1, you have your y-intercept at 1, rises up 2, down over 1, and again, and it looks like this. Pretty simple. This should all be reviewed as of right now. So pretty much what this means is the y-intercept is where the line touches the graph when x equals 0, and so here it touches at y equals 1. So the next type of function are polynomials. And a polynomial function is in the form an x to the n plus an minus 1 x to the n minus 1 all the way to a1 x to the 1, that's just x, plus a0, where the a's are constants and the x's are, well, your x values. So the domain of all polynomials is the set of real numbers, which is essentially negative infinity to positive infinity. And so the degree of the polynomial is based on the highest exponent. So if you have the equation 4x to the 5th plus x squared plus 4, it would be a degree 5 polynomial because the 5th, the 5, is the biggest exponent, so it's a degree 5 polynomial. So a degree 1 polynomial is actually just a line. It's just a linear model. And then a degree 2 is called a quadratic in the form ax squared plus bx plus c. And we've seen this before because we plugged into the quadratic formula since, I don't know, Algebra 1. And the third degree polynomial is called a cubic in the form ax cubed plus bx squared plus cx plus d. Alright, so those are polynomial models. So this brings us to power functions, which are special case polynomials. It's in the form f of x equals x to the a. Sorry. So it's where a is a constant positive integer. So I'm going to draw a few graphs of different power functions. And we can see that they're just, our normal polynomials that we've seen before, but it's only the x to the a. Alright, now onto another special case. It's where a equals 1 over n. So you have the form y equals x to the 1 over n. This is called a root function. An example of this would be y equals x to the 1/2, which is also equal to the square root of x. So this graph would look like this. And this is also equivalent to saying y squared is equal to x. And so now the final type of power function we're going to look at is where a is -1. This is called a reciprocal function. So y equals x to the -1, which is also equal to 1 over x. So what does this look like in a graph? It looks like this. Right? This function is very important in physics and chemistry, and one application in physics is Boyle's law, which states the volume of gas is inversely proportional to pressure. So what does this look like? It looks like V is equal to C over P, where C is a constant, V is volume, and P is pressure. Right? Moving on. Now onto rational functions. A rational function is a ratio of two polynomial functions. So it is in the form of f of x is equal to p of x over q of x. So and it's called a rational function because it comes from ratio of p over q. So you have your f of x is equal to p of x over q of x. So the domain of these functions are where q of x cannot equal 0. So pretty much the bottom cannot equal 0 because anything over 0 is not okay. We don't really know what to do with it at this point in math, and we don't want it. So an example of this is f of x is equal to 3x to the 5th plus x plus 1 over x squared minus 4. So now its domain, because the bottom cannot equal 0, is going to be x cannot equal plus or minus 2. Right? Because if you plug in 2 here, or -2, that will equal 0. So its domain is everything except x cannot equal plus or minus 2. Now we are on to some trig functions. And we all know trig functions from pre-calc, sine, cosine, tangent. And we'll just look at them briefly. Alright. Just a little tip. In calculus, we use radians as a system of measurement. Say goodbye to degrees. This isn't geometry after all. So now with sine and cosine, they both have domains from -infinity to +infinity, and ranges from -1 to 1. So let's look at their graphs. So we can see from these graphs that they don't go above 1 or below -1. So that means that their range is from -1 to 1, but it can take any x value from -infinity to +infinity. So it's an important property of sine and cosine is that they are periodic functions and have a period of 2 pi. This means that sine of x plus 2 pi is equal to sine of x, and cosine is equal to cosine of x. And as a little refresher, I'm just going to draw a piece of the unit circle just so you guys can remember the coordinates. So that's pi over 3, pi over 4, pi over 6, and their coordinates are 1/2 root 3 over 2, root 2 over 2, root 2 over 2, and root 3 over 2, 1/2. So there's the unit circle. You should remember it, but it's good to always refresh on that. Now onto the tangent function. It's a little bit different because it is similar to a rational function where it is one function over another. Tangent of x is equal to tan of x is equal to sine of x over cosine x. So its range is actually from -infinity to +infinity in this case. And its domain is a little different. Its domain is equal to everything except when x equals pi over 2 plus a times pi over 2. So essentially what that means is whenever cosine is 0, function is undefined, so it can't have it, it's not in its domain. So the graph of tangent looks a little different, actually very different from sine and cosine. Looks like this. And these asymptotes would be where cosine equals 0, so we can't have it, there's an asymptote, it's not part of the domain. Finally, onto exponential functions and logarithmic functions. I'm sure they're everybody's favorite functions. Alright, so exponential functions, have the form f of x is equal to b to the x. Right? So f of x times is equal to 3 to the x would look something like this, where 3 is at 1, and that's 0, 1. So now on to logarithmic functions. They have the form f of x is equal to log bx. So, looks a little different. Give me one sec while I erase. Alright, so they have the form f of x is equal to log bx. And so where b is a positive constant, these functions have a domain from 0 to infinity and a range from negative infinity to positive infinity. So y equals log 2x would look like this. Y equals log 3x would look like this. And as you can see, the curves are getting a little bit shallower every time. So y equals log 5x would look even flatter like that. So that's all for the lecture portion of the video. Thanks for watching. I will be back in a few with a few questions to do, and then I'll have the suggested homework in the description of the video. Thank you. Alright, now on to the questions. We're going to be doing number 1 and 19. So the first one, it's asking classify each function. Pretty much what that's saying, tell me what type of function each function is. So for A, we see it's log 2x. Well, this one's pretty simple. As all of these, they're all pretty simple, but it's good to know what type of functions they are right away. So you can be able to recognize the function right away and then move on to the problem. So you see log 2x. Well, you know it's a logarithmic function because it has log in the name. Now on to the second one. You have the fourth root of x. Well, that should have given it away right away. Because if it's the fourth root of x, then it means it's a root function. Again, given away by the name. So now on to C. 2x cubed over 1 minus x squared. One polynomial over another polynomial. So it is a ratio of 2 polynomials. That is a rational function. Again, given away by the name. So this one is a rational function. And bonus points if somebody puts the domain of the function in the comment section below. Now, on to D. You have 1 minus 1.1t plus 2.54t squared. Well, you see you got your t and your t squared, so you can know it's a polynomial. If your input variable is to any power, you know that it's a polynomial. And your t is squared, it's to the second power, so you know it's a degree 2 polynomial. If it was to t cubed, then it would be to degree 3, as we went over in the lecture portion. But so for this one, it's a second degree polynomial function. Alright, now on to E. You have 5 to the t. So we know that as t gets big, 5 to the t is going to get exponentially big. So as again, I gave it away with the name, but this is an exponential function. And you can tell when an exponential function is an exponential function because it's always going to have some number to your input. So this one is 5 to the t, And if you remember from the graph, this will get exponentially big. So when, it'll just get exponentially big. So it's an exponential function. Now on to f, sine, cosine squared, or sine theta, cosine squared theta. Well, it's a trig function. You see sine, cosine, or tangent, you know it's a trig. You know it's trig. We've been told about trig since pre-calc, so we know it's a trig function. Now on to number 19. At the surface of the ocean, the pressure is 15 pounds per inch squared. Below the surface, the pressure increases 4.34 pounds per inch squared for every 10 feet of descent. A would like you to express the water pressure as a function. So what we need to do first is we need to find our x variable and our y variable. So we can tell that as our descent increases, the pressure increases. So that means that our descent would be our x variable, because that is our explanatory variable in statistics. And that's pretty much causes the change. So as descent increases, pressure increases. So we know our x is equal to the descent. And our y is the pressure. Now we have to make a function. It's going to be a linear function because there is no, it's just a line. As descent increases, pressure increases linearly. So we have our fancy little line equation, y equals mx plus b. So now first let's get the slope. What's the slope? Well, we know pressure, our rise, increases 4.34 for every 10 feet of descent. So our run is 10 feet and our rise is 4.34. So if we were to just make that as a slope, we would do 4.34 over 10x. And that can be rewritten as 0.434x, because you can just get rid of the 1, move the decimal over 1, and it is 0.434. Now, what is our b? Well, that is when our x equals 0, so our descent equals 0. So that would be at the surface of the ocean. And it's given to us at 15 pounds per inch squared. So now we have our function y equals 0.434x plus 15. So now part B is saying at what depth is the pressure 100 pounds per inch squared. So now we have a y we have our y at 100, so we set the function 100 is equal to our function because we're trying to find our descent, we're trying to find our x value. So we do 100 is equal to 0.434, x plus 15. So, and then we just solve for x. We subtract 15, and then we divide both sides by 0.434, divide by 0.434, and then we're just going to do this on the calculator, and we're going to get x is equal to, so obviously 100 minus 15, that's obviously 85. You don't have to do that on the calculator, it's simple, but then you do 85 divided by 0.434, and that will give you 195.85. So you can see 0.85, you can see that the pressure will be equal to 100 pounds per square inch when your x descent is 195.85 feet. So that means when you are 195.85 feet below sea level, the pressure on your body will be 100 pounds per inch squared. Alright, so those are the questions that I'm going to do in the video. Thanks for watching. There will be more suggested in the description of the video, that just good questions that I think you should do, and all the answers will be able to be found at the back of the book. So my name was Logan. Thanks for watching, and have a great day.